Good afternoon, everyone. My name is Kumar Rajvanshi. Currently, I am working as a senior research fellow at Department of Mathematics and Computing at IIT Dhanbad. I'm excited to present our work on MIPW and R package for generalized estimating equation with mixing data using multiple imputation and inverse probability weight. So the objective behind for building this package is that to provide a solution to tackle missing data in longitudinal studies, while our model of interest is a marginal model. To set the stage and to move forward our presentation, first, what is longitudinal data? So basically, in longitudinal data, what we do is we collect measurements from same group of subjects over a period of time, and we take repeated measurements from each subjects. So this allows researchers to study within subject changes, trends, and temporal patterns. Such data are common in biomedical, social, and behavioral research. For example, tracking patients' biomarker level, treatment response, and disease progression. So longitudinal data often exhibit correlated measurements, making standard statistical methods inadequate. So in longitudinal data, generalized estimating equations are commonly used to handle the correlation structure among repeated measurements of obtained from different subjects. So why MIPW? Basically, longitudinal data are especially prone to missing data due to missed fits or dropout over time, loss to follow-up, and non-response to specific questions or measurements. So standard GE packages available in open source network R generally ignores or deletes missing cases. So there are three types of missing data based on the probability structure of the indicator variable R. First one is missing completely at random. So the probability distribution for the indicator variable doesn't depend upon the complete or incomplete observations. So missing at random, missing at random. In missing at random, the probability structure of the indicator variable basically depends on complete cases only or observed part of the data. And in missing not at random, the probability structure may depend upon not only the complete case or observed part, it may also depend upon the incomplete part of the data set. So how missing data can impact our study findings? So improper handling of missing data can lead to bias estimates, and it can reduce statistical power of our analysis, and it provides invalid inferences. So what are the solutions? So mainly there are two types of solutions which are frequently used, multiple imputation and inverse probability weight, to which it helps to correct the bias under uh, different missing data assumptions. So multiple imputation and IPW techniques are central to our MIPW package. So these are some of the references which references or literature which extensively studies the case of handling improper handling of missing data in different real life scenarios. So basically, this table shows different packages available in R to fit the marginal model in longitudinal studies, how it handles missing covariate cases. Uh, in the first two packages, G and GEPAC, completely ignores the missing covariate cases, and the second and two packages they are GEE and WGESEL basically uses partial weights to mitigate the bias due to incomplete case. Our package MIIPW successfully integrates the multiple imputation and inverse probability weight technique to cover the missing covariate uh, cases in marginal model. So what is marginal model? Basically, it is also known as generalized estimating equation framework, where we model the marginal expectation of response variable Yij, which are observations collected from subject I at different time point j, and mu ij is the expected value, and z mu ij equal to eta ij. It represents g is basically the link function for the mean structure, or it basically represents the mean structure of our response variable yij, and eta ij equal to chi ij t beta is basically the regression coefficient parameter of our marginal model, and chi ij represents the different covariates of our model. So unlike mixed effect model, G focuses on population average effects, where mixed effect model basically focuses on the subject specific part of our subject specific part of uh, any longitudinal study. So what are the key assumptions in marginal model? We basically define a correlation structure of the error terms, which may include sources like independence, exchangeable, autoregressive one, or unstructured. So in GE model, we do not require any full distribution structure of our response variable yij, and and uh, and another thing is that only mean and variance structure are needed. So main objective of fitting model is how to estimate our model parameter, how we get the estimate for our model parameter, which could be more efficient, more consistent in terms of the various statistical properties. So in a marginal model case, we obtain the estimate of the output parameter beta by solving this estimating equation shown in this slide, and where S represents the score function values, and these are the different mathematical terms. I will not go much deeper into the mathematical part of the model. So this estimating equation can be solved using different optimization technique like Newton-Raphson, Nedler-Made estimating equation, Nedler-Made optimization methods, and all these are basically available in easily available in R computing environment. So in case of missing data, how what happens is that we generally have to exclude the incomplete observations because we do not get the score functions values. So what we offer in our package, we offer three different solutions. We can use mean score, we can use IPW, or we can use AIPW. So what we do in mean score method is that we replace the missing score function values with an expected score function values. This expected score function value is basically obtained from a multiple imputation model where we create multiple data sets with different uh, uh, entries in incomplete observations, and from each data set we obtain the score function values for those incomplete cases, and we get the average of that and use as a estimator for the incomplete score part of our estimating equation. This is the framework how it works. So once we once we done the multiplication part, we use those using those score function. We modify the estimating equation initially used to estimate the parameter beta. So this is how we get the estimating equation for mean score method. By solving this equation, we obtain the unknown parameter below beta under mean score method. So in other two methods we offer in our package, IPW and AIPW, we use inverse probability weight as a obtained from a probability model represented by this probability distribution P delta ij equal to 1, conditional on yij, xij, and xij. This, but in our estimation part, we use MAR condition. So in our probability model, we use only the observed part yij and xij, not the xij this part. Visible, and we get the pi ij values and use it into the estimating equation we obtained earlier, and by solving this estimating equation, we get the IPW estimator. At last, in case of AIPW method, what we do, we use the multiplication part for getting the missing score function values, and use the probability selection model to obtain the IPW part. So at last, the estimating equation for AIPW method becomes like this when we use IPW and mean score, IPW and multiple representation part in our estimating equation. So after fitting different types of models, what we do is we try to select which model is good for our dataset. So this could be done using quasi inversion criteria in case of marginal estimating equation for longitudinal data. So these are the two formulas how we calculate the QIC values for our model. So what we offer in our MIPW package, we offer 5 different estimating functions for estimating the unknown parameter beta, mean square, SIPW, AIPW, miSIPW, miAIPW, which are compatible with 4 different correlation structures, AR1, exchangeable, unstructured, and independent. Different inputs or different arguments used in our functions can be divided into 3 parts. First, these 4 arguments basically defines the data structure and model for our GE model. These 2 arguments, family and correlation structure, basically defines the properties of response variable Yij, and this 6 arguments basically controls the optimization part of our model parameter estimation. First 3 arguments basically defines initial values for beta, alpha, and phi, which are regression parameters, correlation parameters, and dispersion parameters for our model, and which defines the IPW part of our model used in different functions. And tolerance and maximum max IT basically controls at which point we will stop our loop for the optimization part. So our functions are easily or flexibly integrated with mice package through mice functions, and pmet argument used in different functions in our package basically defines a predictor matrix which is similar to the predictor matrix used in mice package, and it supports different methods available in mice package through the mice functions internally in our different functions. So these are the basic syntax of 3 different functions, mean score, IPW, and AIPW. These are the 3 arguments, M, pmet, and method, generally defines the multiplication part, and QIC, MIPW functions available in our package helps us to find the QIC value, where first argument is basically a correlation GE model with correlation structure R, and second model is GE model with correlation structure independence, and family basically specifies the distribution like Gaussian, binomial, or Poisson for the response variable Yi, J, or in our model. So this is a short tutorial to show how these functions can be used in real life dataset. In our package, we have included an dataset named SI.1 example. This is basically an example dataset. So these are 3 steps before fitting the model: data preparation, model fitting, and model comparison using QIC. So these two lines of code basically loads our package MIPW and loads our dataset SI.1, which is a longitudinal cytopin data, and it contains repeated measures per subject ID at different type points, which are represented by the visit column in our SR.1. So our outcome variable of interest is C6, which is the inflammatory biomarker. So this two lines of code, M1 underscore formula basically defines the Z model formula, where C6 is the response variable and others are the active in R1B, active in R2B, active in R2AB. All these are covariates which we are interested to include in our model of interest. So PMAT basically defines the predictor matrix, and it is obtained from the mice package make.p predictor matrix function using make.predictor matrix function. And so this is how we can fit a mean score model. So first we define the data set using data argument, which is a SR.1 formula, M1 underscore formula, which defines the G model formula, and M equal to 2 defines the number of multiple imputation part we are using for estimating the score function values in our G model. So similarly, we can use this kind of syntax for fitting the SIPW and AIPW functions for our G, similar kind of G model, which we are using through the formula argument M1 underscore formula. So at last, QIC MIPW function uses the two models M1 and M11. First model M1 uses the correlation structure auto reduce of 1, and M11 uses correlation structure independence, and we consider the family argument to be Gaussian, and it gives the QIC values to compare these two models, whether M1 is better than M11 or not. If we get a lower QIC value, then we consider that correlation structure is better for fitting our model. So our functions, our package is already available in CRAN, and it is fully documented and with a good help page, which is nicely written help page, and it integrates with mice package, and summary and print functions usually are quite helpful for researchers to get a quick results, which are also available in our package. So these are the key takeaways for our package of MIIPW, or and it is the first R package which successfully integrates MI multiplication and IPW. I'd not say it completely solves the problem of missing data, but it gives a wide variety of estimation methods for researchers to fit the marginal model in longitudinal studies. The R package is designed for medical researchers, or initially we designed it for medical researchers with minimal coding. These are our objectives initially. So that's it. Thank you, Augmentation 2025, for giving us the opportunity to share our work in such a wide community. And these are my special links. If anyone like to discuss anything or have any doubts, please, I'd be happy to take any questions. Thank you.
Great, thank you so much. I think we have time for maybe one question. Ben Gerber asks an interesting question in chat. Looks like this targets generalized estimating equations. Can this be extended to mixed effect models with longitudinal data?
Thanks, Ben. It's a good question. So we are trying to extend it using linear mixed effect model. The main problem in linear mixed effect model is handling different random effect terms, which requires very much computation time. So we are in future we are looking forward to extend it in case of linear mixed effect model.
Excellent. Thank you so much. This was a really interesting chat, and thank you for presenting us your really well documented and successful package. It's not easy to get a package on CRAN, so congratulations on this fantastic work, and thanks for sharing it with us. Thanks so much, everyone,
Thank you,
for
guys.
attending. All right.